What I really want to focus on here, though, is security, and by that I'm specifically looking at people on the internet trying to break your web applications. I'm mostly worried here, particularly about opportunistic attackers. People going out, randomly looking for easy, obvious breakages in your systems. I'm not too worried about nation states, and I'm mostly focused on the case where you're slightly smaller. It's quite easy to assume, if you're not Twitter, GitHub, Facebook, or Google, say, that you don't have to worry too much about security. It's very common for a lot of people to leave this as a problem to solve later. We're not going to deal with it. If you look at the whole of the Internet of Things track yesterday, for example, there is a lot of people not thinking about security for now. And while that's good for getting prototypes and stuff working, there is a lot of value to breaking the security of small applications like this. And if you are obviously easily vulnerable, people are going to do it. Your stuff is going to break, and you are going to lose lots of money. Even if you're quite small, you can become a platform for virus and malware distribution. We've seen customers who turned up and their servers were quietly mining bitcoins, phishing attacks. There's lots of different ways to break systems, even if you're a relatively smaller player. I'm assuming for the purposes of this talk, you're writing code, something like this. You've written some code, and you've got a bunch of tools behind the scenes that are helping you run that. The core thesis I really want to hit home here is that everything in this is broken. Security is really hard, and nobody really successfully pulls it off. You look at very big players like Google and Twitter and GitHub and Facebook, and they fail. Security bugs come out even there. They have teams of security experts working very hard, full-time, some of the best security experts in the world, and they fail. You are less good than them. You are going to fail as well, and everything you depend on is going to fail. Security is really hard, and this changes how we think about this. Instead of focusing just on how to make your code secure, while that is still a very good and worthy goal, it's also useful to focus on how you can limit the damage once security issues turn up, how we can mitigate and manage the risk, how you can recover quickly once inevitably everything bursts into flames. There is one upside to this, which is that most of the time, if you're not doing something fairly stupid, the efficient, easy, efficiently breakable thing in your system is not really your code. As an attacker, it takes quite a lot of effort to understand your specific system and break it. Whereas if I can find a vulnerability in Apache or in Java, I can break thousands, millions of live systems. Often I don't even have to find that exploit myself. These are published, and all I have to do is find one of these online and start trying out in places. And if you've got these easy vulnerabilities, this is where your system is going to start to really fall down and where you feel the pain. So what we're going to do in the rest of this talk is look through a series of exploits for these kind of things, a series of holes and problems and ways that your tools can totally destroy everything you love. This does bring us to a first immediate conclusion, which is that you have to be ready to update when this stuff comes down. You need to be on the security notification lists for all the major tools that you're using, for your databases, for your languages, for whatever web framework you've got in place. You need to ensure you are getting notifications as soon as problems come up in that. And once you get those notifications, you need to be able to get that update ready and put it live very quickly. If an exploit comes out an hour from now for the web framework you're using, and there is already information on the internet for how to break your system, you're in a straight race between somebody copying and pasting something and pointing it at your server, and you updating your web framework, testing it and ensuring it's good enough to put live, and doing a production deployment of the whole of your system. You have to be ready to get this information quickly when it comes in, and put it into action and get it live. And if you do nothing else in this talk, if you go to sleep in 5 minutes, make sure you're in a position to do this. We'll start going down through this with Rails. Any Rails developers in the room? Any Ruby developers? No. One Ruby developer. OK. So Rails is a web framework. It makes managing lots of the complexity of web apps very simple. It's very nice. It's very quick. In the Rails world, YAML is pretty popular. It looks like this. It's more or less a superset of JSON. Braces become optional, and you can use indentation instead. But we're describing the same sort of structures as JSON. It's also got a load of strange and interesting features, like typed YAML. Here, if you pass this document, you don't get given a tree structure of nodes and data, as you might expect if you pass a document. Instead, you get given an instantiated user object. That might not be what you expect. This means you can pass YAML and get given a thread, or a database connection, or all sorts of other weird stuff, and makes YAML feel quite scary and dangerous. This isn't quite as bad as it sounds. Internally, the Ruby for this looks like this. We don't call the user class's constructor here. So we don't actually run the user class's code. What we do is do user.allocate, which creates a blank, empty object that's the right shape. And then we manually set each field one by one, taking the keys and values out of the YAML document. So setting the name property to the name and so on. So in principle, this doesn't run any code. This generates an empty data structure of whichever class we're looking for. And that feels still a bit weird, but slightly safer. Unfortunately, though, Ruby's quite powerful, and in Ruby you can override the key equals value operator to call a method and pass the key and value to that. And if somebody had implemented a class which called a method that took this key and value and did something dangerous with it, trusted that, then by passing a YAML document, by just trying to look at the structure of a document, you might accidentally end up doing all sorts of crazy, dangerous things. And there's a specific case where this went very wrong. In named route collection, this is part of the routing infrastructure that handles where traffic goes inside Rails. The details don't matter too much, but critically we override the key equals value operation, and we pass the key and the value from wherever it comes, here, the YAML document, as the name and the route to add, and then we eval a string, and this hash brace's name is string replacement in Ruby, so this gets replaced with the actual value of name. We'll bring all this together in a second, but essentially this means if we can provide a name here that runs some code and get it to come through here, then by passing a YAML document, we can run code. A string might look something like this. So we do ignored semicolon and terminate the current expression. We put whatever code we want to run. Here we print hello, but we could do anything. And then we use this end keyword on a new line, which is a weird Ruby feature that just stops processing the rest of the file. I'm not sure why that exists. If we do this transformation, we end up with this string, remove possible method ignored, which does nothing, print hello or anything else, delete this database, steal all your password hashes, start monitoring all the traffic going through, or just connect back to the attacker and await further instructions, anything at all, and then we comment out the rest of the string. If we can get this string into that add function, then we can run whatever code we like. And a very simple YAML document to do that looks like this. It's fairly short, and it's terrifying. If you pass this, it says, I want to build a named route collection. You should set this key to this value. And the key is that terrifying string, and the value is an open struct. This is just an empty object that gets us past some validation. If you can get the default Ruby YAML parser to pass this, you win. You can run whatever code you like on that server. You can replace put hello with any Ruby and run arbitrary code on the server. This is bad. You would hope that this would mean people would be quite cautious about how they use YAML, and you would never, for example, pass YAML that was given to you over the internet by a stranger. Unfortunately, though, that has not been the case. In early 2013, it was discovered that you could do this. In any XML, you could put type equals YAML on an element, and then you could just put YAML in it, and it would pass it. Rails accepts, at the time, accepted XML by default to any endpoint, and this was enabled and available on every Rails server running in the world. And overnight, every Rails developer discovered that anybody could copy and paste this very short snippet and run arbitrary code on their servers. This is not a good thing. this is a stressful time to be a Rails developer. If you get an email an hour from now telling you that something like this can happen on your system, you're going to be upset, you're going to be stressed. You're going to have to really, really quickly update to the new version of Rails before somebody else tries this on you. Get that pushed out, get that ready, and get that live. And then there's going to be endless recriminations, and how do we deal with this better? And the business is going to be concerned about all the risk that's coming in here. And then, unfortunately, 2 weeks later, it's going to happen again. Here in JSON, which again is enabled by default on all Rails servers for all inputs, it turns out the JSON parser that Rails uses is not a JSON parser. It's actually a YAML parser that assumes it's given JSON. All it does is take a string, assume without checking at all that it is valid JSON, do the minimum required transformation to ensure that if it was JSON, it's now valid YAML. And actually all this is, in practice, is it puts a space after the colons between keys and values. And then it passes it as YAML. So if we pass a bunch of YAML and we swap the colons for the Unicode equivalent here, and we then set a content type on our request and promise it's JSON, the YAML parser will trust us completely, pass it as YAML, and we'll delete the database and run away with all the money and so on and so forth. And again, stressful time, especially only 2 weeks after the previous attack. Up until this point, Rails had a reasonably good reputation for security by and large, and suddenly people were quite upset and quite frustrated, and they hadn't had much sleep. And then 2 weeks later, it happened again. Here in Active Record, the ORM within Rails, so this is a slightly different case. I won't go into the details too much, but there's a serialize feature that, again, uses YAML, again, overtrusts the input it's being given, and allows you to pass inputs to Rails servers using standard basic features in standard recommended ways, and do whatever you like with these servers. This is bad. If you're a Rails developer, this month, this was January 2013, I think. January and February, over a 6-week period, your entire system was totally exposed 3 times. This is the kind of thing we want to avoid, and this is the kind of thing that is not actually that rare, and we're going to see a whole selection of examples where stuff goes horribly wrong. And the best thing you can really do to try and deal with this stuff is stay up to date, and is try and limit your user input. Basic user input validation is obviously something you should be doing in your code. Trusting input from users is very foolish. But we can go much further than that here. These endpoints are accepting JSON and XML by default, just in case that's useful. We're being extremely liberal in the input we're going to accept, even though we don't really need that. Most of these servers were not using XML at all. I think nearly nobody was using YAML within XML, because why would you even want that? We're being extremely liberal in all the kind of different inputs that we'll support. If you can instead lock your input down, absolutely limit it to stuff that's reasonable, especially in cases like this. This is an API. You've got a good understanding, by and large, of the requests that are going to come in from your API. It's not people typing stuff into the internet. It's automated systems. You can be very strict. If you are very strict and you limit the input, you drastically decrease your attack surface. You reduce the number of ways somebody can poke you and see what breaks. The less input you accept, the more you just outright reject, the safer you can become. PHP. Anybody ever written any PHP? Couple of hands? Quite a few hands. Okay. PHP is very big. It's very popular. It runs more websites than anything else, I believe. Wikipedia, Facebook, WordPress. It is absolutely everywhere. In PHP, for quite some time, this was the recommended way of writing code to create a new user. Somebody submits a username and a password. You save the username. You hash the password with some salt. And then you put the user into the database. The crypt function that does the hashing here is a bit weird in PHP. It doesn't just return the hashed password. It returns the hashed password, followed by $, followed by the salt you used. And this is so that you can pass it to crypt later on, and it can extract the salt back out for you, because that's a bit convenient, and it means you don't have to save the salt separately. It's a bit weird. Once you've done this, if you want to do login code for, in PHP, again, the recommended way straight out of the docs is to do this. Somebody submits a password. You get the previous password from the database, and you're going to use it as the salt, because it's got the salt in it. And you pass that as a second argument to crypt. And you get the password they submitted. And then you see what the hash comes out with, and you check that you end up with the same thing. In PHP 5.3.7, an important security update, which was live for 5 days and downloaded and installed into millions of PHP applications. PHP is big and huge and everywhere. A well-meaning PHP developer made this one character change, moving from stir ncat to stir lcat. This is in C. This is the internals of PHP. This did not do what they thought it did. This is 2 ways of concatenating strings together. And in both cases here, we're trying to be secure. We're trying to avoid reading off the end of null-terminated strings, which is a risky, tricky thing to do in C, potentially. So the first method here, stir ncat, takes a third argument, 1, which is the length of its second argument. This is to double-check that to make sure that you can't accidentally read off the string and get all sorts of exciting buffer overflows and so forth. Stir lcat, meanwhile, takes a third argument, which is the length of the total string you're expecting back, including the null terminator. Here, we concatenate the password with a $, and we always return the empty string, no matter what those are. That gives us this fun invariant. Anytime you hash a password with a salt, you just return the salt. If we take the recommended login code directly from the docs used by a lot of PHP applications, and we apply this invariant, this code becomes this, which becomes this, which is always true. If you updated to this important security release, which was up and recommended for 5 days, all of a sudden, anybody could log into your system with any password. Who here has integration tests that check you can't log into your system with the wrong password? Indeed. It's very easy to not notice this, but there will be people on the internet who will try and log in to your account, to other people's accounts, and guess passwords, and all of a sudden, they'll be right. They suddenly get access to all sorts of things, and your security really falls down. And it's very easy not to notice. This PHP version is still live in quite a few places. Years later, you see Stack Overflow questions asking why crypt doesn't seem to work properly in this version of PHP. There are a lot of PHP users out there, and once you release Made software like this, it doesn't go away. It begs some very interesting questions, though. Did they not have tests? This is the kind of stuff that you can test well, right? You can write good unit tests for this kind of hashing code. And they did. They've actually got some very good tests that catch exactly this error, show where the problem's happening, and nobody ran them. The developer who made this change did not look at the results of these tests. The developer who bundled this up and shipped it in a release to millions of PHP developers did not run these tests, and nobody noticed for 5 days that unit tests in critical security infrastructure of a major language were totally failing. Perhaps somebody else might have noticed outside the PHP team. Perhaps this might have been reported somewhere. It was. 2 days before release, somebody filed a bug pointing out exactly what was broken, exactly how this was going to fall down, and that maybe we shouldn't release it as it stands. And nobody really looked at that bug for 7 days, 5 days after release. This is pretty bad, right? The really key thing here, I think, is that nothing the PHP team really needs to do to make this work is news. Running tests, having a bug tracker that you look at. This isn't controversial, crazy stuff. But it is stuff that they weren't really doing. A lot of people assume best practices exist primarily for your own productivity, to help you as a developer get stuff done better and quicker. That's true, but they're also adding direct business value to your product. Secure software costs you way less money, or more accurately, insecure software is extremely expensive. These kind of best practices not only help you build stuff better, but will actually build better software in the end. Focusing on these when you're writing your own software will help you avoid these situations. Also, looking at the tools you're using and trying to focus on this will add value. If you're considering a tool, see if it's got a good suite of tests. If it doesn't, you open yourself up to exactly these kind of issues. See if they're running the tests and they pass. Have a look at the culture of software development behind the tools you use to understand whether you're going to be opening yourself up to these sorts of security issues. Jetty. Anybody using Jetty? Yeah. Cool. Jetty's pretty popular in the Java language, Java world. It's pretty good. It accepts HTTP requests like this, for example. Notably, in HTTP requests, often you have some secrets in your headers. There are some things that you would like individual users to keep private. You don't want users to be able to read other users' HTTP headers. That would be bad. This is an invalid HTTP request. You're not allowed to just drop UTF-8 characters into the names of your headers. If you do that, servers will give you errors back, and Jetty, for example, for 6 months between between September 2014 and February 2015, would give you this error back. This is quite an interesting error. It includes the start of our request, the broken character in our request with a nice little arrow and some bits of context, and then a whole bunch of zeros. So this is a bit weird. Where are these coming from? What's going on here? What's actually going on here is that the developer who set this up used a generic print me a nice debug string of this buffer method, which gives you lots of good debug data about what's going on in the buffer. This is Jetty's request buffer, and this gets reused between requests. If you send a request that's shorter than the previous request, some of these zeros will have data in from the previous request that came into Jetty. And we can exploit that, and we can read other people's requests, again, in a version of Jetty that was live for 6 months. If you make this request on the left, and then subsequently somebody makes this request, again with a little Unicode character in it, they get an error back pointing out that they've made a mistake in their request, and here's a bunch of bytes from the previous person's request. And we can start reading bits of secrets. We can actually shift around which bit we're reading by just adding an extra little bit of padding, and if we do this in quick succession, we can read out whole chunks of other people's requests, and quite quickly you start to see lots of secret information leaking here. Nowadays, Jetty returns this. Concise, very simple, less useful for debugging, vastly more secure. You have to worry about the security context of the kind of information you're returning here. And there's a conflict as a developer. Having really good errors that tell you exactly what's gone wrong is great for working out how your system works. It's also great for everybody else on the internet working out how your system works. You can have errors that expose actual user data, like this, which are quite bad. Even more generally, errors that expose exactly what exceptions come back from your SQL, exactly why specific details of your validation have failed, all of this kind of thing makes it easier to work out how to break your system. Extra information you're exposing here opens up advantages, makes it easier for attackers to understand what you're doing and to break it. Focusing on the security context of the information you're returning, how secure it is, who you're prepared to let see that information, and limiting these errors helps you reduce that. You can log to files on the server instead of returning detailed errors like this. You can have detailed errors returning only in development mode instead of production mode and so on. All of these practices are absolutely key to trying to reduce the damage and exposure from this. Postgres. Postgres users? Anybody? Yeah. Postgres is great. Postgres does loads of awesome stuff. This is going to be a sad tale, obviously. If you wanted to connect to Postgres on the command line, you might do something like this. You'd specify a host and a database name, and it would connect. That's great. In probably the most absurd bug of the lot here, it turns out that from late 2010 to the middle of 2013, if you specified a database name that began with a dash, it was not interpreted as a database name, but as a command line argument to the server. That means you can do this, where the database name is -r with a path, which writes the command output to a file. Here, we write whatever output of the command happens as a string to the end of our database, our big binary database, and this corrupts the database. Immediately, the Postgres server shuts down. This is amazing and pretty bad. Critically, this actually happens before authentication. So if you're depending on the authentication in your Postgres server, you're totally screwed. This happens before any kind of security in Postgres, before connection filtering on IP, anything whatsoever. If you've got a connectable Postgres that was set up over these 3 years, you can connect to it and you can turn it off. The actual error that gets written in this case, looks something like this. We're trying to connect to a host where the name isn't quite right. And this is the username. You tried to log in, and this was the database. We can write this using this argument to any file on the system, and we can control some of the data in here. We can change the username parameter, particularly, while keeping the attack still working. This means we can start looking at the same kind of injection attacks that we were looking at with Rails earlier. If we can put this somewhere executable, and we can change the user to some code that we want to run and format it right, we can get it so that this attack actually becomes a way to run arbitrary code on the Postgres server. And as it turns out, we totally can do that. If we write to the .profile file, then we can write code which will be run next time the Postgres user logs in. And the .profile file is extremely liberal about what it'll run. If we put some gibberish in there, it'll skip that line and it'll run the next line. So if we provide a username that starts with a new line and then has a hash to comment out the rest, then we can put any code we like. And again, we can steal the database, shut the server down, connect back and run arbitrary commands, anything at all. This isn't quite right bash syntax, but you can, with a bit of fiddling, make the equivalent requests that would do exactly this. If you do this, you end up with a profile file that looks like so. There's a line of gibberish, and there's a new line that prints hello, or anything else. Next time you log in as Postgres, it complains about the gibberish and prints hello. This means you can make a single request to any connectable Postgres, and next time the Postgres user logs in, you can run arbitrary code. You have to wait until they log in, but it turns out if you connect to a Postgres instance and you corrupt the entire database, the first thing the system administrator is going to do is go and log in. And as soon as they do, you can run whatever you like. This is pretty bad. This requires that your Postgres is connectable. You have to be able to actually hit it. You would hope that perhaps that wouldn't be an enormous problem. Perhaps people don't run Postgres that are accessible directly on the internet. Unfortunately, they do. According to Showdown, there are 500,000 Postgres currently connectable on the default port. How many of these were set up between 2010 and 2013, do you think? Lots of them, I'm going to say. There's a lot of different reasons for this. Cloud services particularly really encourage this kind of stuff. Heroku, I think, gives you publicly accessible Postgres instance with every different site. And Heroku actually have somebody on the board of Postgres and managed to get early notification of this and patch it in advance, which was good, or they would have been seriously screwed. So there's all sorts of different reasons for this. It's naivety, it's convenience, but it makes you extremely vulnerable. Trying to focus on isolating your components so that you're not depending on the security of just one thing reduces this risk. If you have a firewall around Postgres, which is filtering which IPs can connect, for example, and you have authentication on your Postgres, then you are only screwed if they both fail. And that will happen much less rarely than one of them failing. You can increase your security by combining the security of these, by building layered security. Similarly, if your internal components aren't isolated from each other, you can make this worse. If your Postgres instance is running on the same server as your web server, then potentially I can go from this to also cracking the web server and seeing passwords as they come in, stealing SSL certificates, whatever. If they're running as the same user, that gets even more likely, even worse. Trying to isolate your internal components from one another means that when stuff breaks, not everything breaks. You can think of it like ships, where you've got bulkheads within it. When you knock a hole in the ship, one part of the ship floods, but the whole ship doesn't sink. You want to try and limit the damage, isolate how far these kind of attacks can go by separating your components from one another. Last example then, bind. Bind runs DNS. Essentially, it has about 85% of the market. DNS is fairly key for pretty much everything. We depend on it to run the internet, really. And until strict transport security gets much real uptake, we also depend on it to a reasonable degree to stop phishing attacks. If I type in paypal.com and I end up on a totally different server, which just serves up paypal.com without a certificate, I'm not really going to notice, especially if you're not a software developer. And there are things coming in steadily to try and improve this, but at the moment, we still depend on DNS for a reasonable amount of security. TSIG. Does anybody know what TSIG is? Indeed, nobody knows what TSIG is. TSIG is transaction signatures for DNS. DNS is a distributed database, essentially, and we need to authenticate communication between our nodes. So we sign transactions going back and forth. It's basically obsolete now. This is an RFC that came in 2000, and it's replaced by and large by things like DNSSEC, which do this and a whole bunch of other stuff much better. So this is a fairly obsolete feature. T-key is a niche extension to this, more or less. If you want to authenticate these transactions, you need to have a shared key between the different DNS nodes. Passing that around by hand is a bit of a hassle, so T-key lets you distribute that within the DNS infrastructure itself. You can have DNS records that hold keys, and then you can look those up. And there's some details. This is a niche feature on an obsolete feature. This is the implementation of T-key in bind. It's quite long. It's all C. It's somewhat confusing. There's lots of writing things out to various parameters and interesting special cases. We do all sorts of fun bits of go-toing and so on. There's a bit where we just list every hexadecimal digit, just in case. There's this fantastic line in the security infrastructure that runs 85% of DNS. There's switches with go-tos within them. And critically, there is a crippling security bug. Did anybody spot the crippling security bug? This is complicated and confusing and difficult to really audit and spot issues with. If we zoom in a little bit, this is the particular bit in here that actually looks up the name for a key and tries to get the data. So we get a T-key and name, and we're going to write out to these. This is where our results are going to go. We try and look up the record for that name and write it out to the key in the key set. If we fail, we try again slightly differently to the same key name and key set. And this is a special case for Windows 2000, which nobody uses. Inside DNS message find name, there's a few interesting things. Most interestingly, we can write to the name, we can write our result, and we can then not return success. This means, going back, we can have written to the name when we get here and not get success, so that we call this again with the same name that already has data in it. Unfortunately, in find name, there is an assertion that name does not have any data in it. When this fails, the server shuts down. There's, even better, a nice little comment pointing out that these requirements are probably too intensive. It turns out you can send a single message to this, looking up a slightly distorted message, looking up a T-key, and you can shut off DNS servers. And a security researcher found this and discovered you could essentially very easily turn off 85% of the DNS that runs the internet. This is pretty bad. It's good that we found this by security researchers. Specifically here, this was found through fuzzing, random generation of data to see what stuff you can come up with that breaks things. But you can imagine the kind of consequences if it was found by other people. We really depend on the internet. Most of us here have businesses that don't make any money if there's no internet. Banks, government services, all of this stuff runs on the internet. And if overnight somebody turned it off, it would be very painful. Critically, this is kind of confusing and complicated. It's very difficult to audit and understand code like this, which is why nobody did. The only way we found it is by guessing things. Reading the code is impractical and impossible to spot these kind of bugs. Bind actually supports 137 RFCs. There's an enormous number of features and complexity within this as software. They do basically everything. This is a niche feature of an obsolete feature with a workaround for an operating system that nobody uses. Once you start building up this stuff, you can see how you end up with huge sprawling code bases that nobody can really understand and that start to fill with bugs. Complexity creates bugs, and some of these are going to be security bugs. Obviously, if you're writing code yourself, chasing simplicity is going to be a good way of trying to improve the security. But if you're trying to pick tools too, pick tools that are less complicated. If you pick a big shiny thing that can do everything, that means you have way more things to break, and everything breaks. Pick small focused tools, turn off features you're not using, and limit what your system's doing to speed stuff up. I want to be clear that these aren't a specific special case of the few bugs that have happened recently. There are loads for everything. All of these have, right the way through the talk, have CVE numbers, common vulnerabilities and exposures. This is a big database of well-known vulnerabilities and issues with services. They come out all the time. There have been 700 so far since the start of the year. 60 of those are 9 or more out of 10. That means they're crippling, they're easy to attack, and they're not special cases. This stuff comes out all the time. It's terrifying as stuff breaks. And instead, trying to work to quickly recover from these issues, trying to isolate components to limit the risk of these issues, and trying to limit how you expose information so they're harder to attack, brings this risk down, allows you to mitigate the damage, allows you to recover faster. That's everything I've got for you today. Again, I do work at Softwire, and we are both recruiting and available for hire if you're interested in any of that. And I'm Pim Terry on Twitter, and I'll be tweeting the slides out later so you can take a closer look. Thank you very much.
Thank you, Tim. We have about 2 minutes for questions. So, yeah.
So the number one thing I would do is subscribe to the security mailing lists for your services so you find out about new problems. For checking existing systems, there's quite a few products starting to do this. I don't know exactly which one is the biggest in the Java world. Gemnasium used to be just Ruby and has been expanding quite a lot, and I think now does Java, and will give you automated, so you essentially give it access to your POM for Maven, say, and it goes through and checks all your dependencies against a list of known exploits, and will send you emails. There's also David DM, which I think will do similar stuff. There's a few options.
My answer to the question, there is OWASP event dependency check. OWASP, Open Web Application Security. And they have a dependency check made for you. That checks all your libraries against CVE database and versions, and it tells you, it gives you a report of all your possible versions.
OWASP also have a whole bunch of other good security information, and if you're trying to learn more security stuff, going in there, they've got a top 10 list of exploits to understand, issues to understand, this kind of thing. It's well worth a look.
I have a question as well.
Okay.
So what do you want to tell us? Not to update our software or to update our software? Because in the PHP case, it was not to update our
So if you hadn't updated, in that case, you'd be vulnerable to the previous exploits. All you can really do is try and keep up, essentially. There's lots of practices to, yes, limit the risk when stuff breaks, but stuff is going to break, and at least being at the reasonably up-to-date end means that the stuff that is going to break is not stuff anybody else knows about yet, which is better than nothing.
Okay, thank you. Time is unfortunately up, but I don't know, are you here for some more questions in the break or so?
Yeah, I'll be around in the break. I have to run off and give another talk in the other room now.
Okay. Yeah.
Do come talk to me later, that's fine.